Right, so here we're looking into the binomial distribution, and there's a fair amount of little points and key points here. I'm just going to get straight to this. And so let's apply these things. Say there's a 30% chance of rain in each of the next 5 days, and the probability of rain each day is independent of every other day. That means, well, when we say there's a 30% probability of rain on any day, it doesn't matter if it rained the day before or not. We're just going to say every day is independently 30% probability of rain. And so therefore we can say the probability distribution, if R is the number of rainy days, it's a binomial probability, which means it either rains or it doesn't. All binomial distributions are about something that is binary, either happens or it doesn't. And N is the number of events, in this case the number of days, and P is the probability of success, which we can't get too hung up on the positive side of success. In this case, it's the probability of whatever we're measuring happening. In this case, it's rain, so it's the probability of it raining. And so I've already given most of the answers to the first part, N, P, and Q. N is the number of events, and so in this case, the number of days. And so for this, N would equal 5, because we say there's 5 days. The probability of success, again, in this case, is it raining, whether you think that is a success or not. And so the probability of success is 0.3, 30%. And that said Q, which we don't always have to mention, Q is the probability of failure, which is just the probability of success not happening. In this case, it's 1 minus 0.3, or 0.7. Failure in this case being the probability of it not raining, which you may find a success, but in this case we call that failure. So we don't want to get too hung up on one having to be an inherent good or a bad thing or anything. And like I said, all binomial distributions are either something happening or not. So in this case, it's either raining or it's not. So there are 5 different combinations of how it could rain exactly 4 times in 5 days. So I want to show that. So one option is just to list it. If you have 5 days, for example, how could it rain exactly 4 times? Well, it could rain 4 days in a row, and then not rain. I'll say be D for dry on day 5. Or it could rain 3 days in a row, be dry, and then rain again. It could rain 2 days in a row, be dry, then rain 2 more days. And you kind of see that if we're just methodical about this, there's only 5 possibilities. So listing them out in this case wasn't terrible, but it's kind of annoying. So 5 combinations, we say. That said, a much faster way is to use this combination notation, which we can say either 5 days, choose 4, or 5C4. Another way of writing it looks almost like a vector. We have 5 over 4. This represents what I've just found. There's 5 trials, 5 events, and 4 of them are what we're looking for. 4 of them rain. And you can calculate this on a GDC quite quickly. And so you should get exactly 5. So keep in mind, whether you're listing them out, which generally we don't recommend because it can get really time consuming, we're probably going to use one of this notation. Most GDCs have a function that looks like that. This is another common way of writing it out. It all represents what you see here, calculating, in this case, the number of different combinations of how it could rain 4 times in exactly 5 days. So if I want to find the probability that it's going to rain exactly 4 times in 5 days, one option is to use this formula that's mentioned on the other side, which I can say the probability of R equals 4 is the number of ways it can rain 4 times in 5 days. So 5 choose 4. Or 5 over 4. Actually, I'll just stick with the first one on the note. Times the probability of success, which is 0.3, and how many times we're having it be successful, which is 4 times. All that multiplied by the probability of failure, which in this case is 0.7, by how many times it would not rain, which is once. So if it's going to rain 4 times, that means it's not going to rain once. All of this, though, can be done on any GDC you should be familiar with, and quite often, for example, in the TI-85, it looks like this. We have the binomial probability distribution function. And you want to be familiar with that. But in general, quite commonly, you first type in the number of trials, which in this case is 5, the probability of success, which is 0.3. You generally don't need to type in the probability of failure because it's just 1 minus that. The calculator can figure it out. And then finally, the number of successes, in this case 4. And either way you do it, whether you kind of use this formula or just speed it up a bit, you should get 2 to 3 significant figures. You should get 0.028. 4 to 3 significant figures. Keep in mind this formula here, I mentioned on this side of the notes, right, where is it? Oh, it's hard to find, right here. But in practice, you won't really need to use that much at all because your GDC should have that same formula programmed in. Again, this binomial probability distribution function, and you're expected to be familiar with when to use it. All right, so next, I have a baseball player with a 0.275 probability that they will hit the ball, or that's based on previous experience. So a 0.275 batting average, and I want to complete this table first of all. And knowing that I have 6 trials, so these, you may notice there's 7 columns, but we say there's 6 trials because if you attempt to hit the ball 6 times, there's 7 possible things that can happen. They'll never hit the ball, hit it once, twice, 3 times, 4 times, 5 times, 6 times. So we have 6 trials, and each time the probability of success is 0.275. So I have the table partially filled out. I want to complete the table. So first of all, for this here, while we could use a formula, I could just use the binomial probability distribution function where we have 6 trials, the probability of success is 0.275, and here we're looking at exactly 2 hits. And if you do that, you should get about 0.313. Do the same thing here, but now instead of a 2, we have a 3. And you should get approximately 0.159. And all the rest are done for us. You could double check, but now I have this all finished, and although I'm not going to take the time to do it, like any probability distribution table, if you add them all up, it should all add to 1. Oh, I just got rid of my work. Shoot. All right. 159. All right. With that said, what's the probability of H being less than or equal to 1? Which means what's the probability of the person hitting never at all, or once, which means all of this added up. That's what this represents. And in this case, since I have the table, the fastest way of doing this is probably just to add these 2 up. And in this case, I get approximately 0.145 plus 311. This is approximately 0.476. That said, while I could do something similar for this, the probability of H being less than or equal to 3, that represents all of this here, any of these, up to 3 and including 3. Keep in mind, it wouldn't take me that long to do it, but it already gets annoying. Plus, each of these has been rounded, so there's a bit of rounding error that adds up each time. So for this, we probably want to use the binomial cumulative distribution function, which on most GDCs looks like this, binomial cumulative distribution function, which means you ask the calculator to add up all these for you. And it's very, very similar how we use this. First, the number of trials is 6, 6 attempts at bat. The probability of success is 0.275. And then the last number is the maximum we're looking at. In this case, it's 3. But if we're using this function, we must realize that it's not actually telling us the probability of exactly 3 hits. It's 3 or anything less. And that's what the C stands for, cumulative. Cumulative means everything up to it and including that value. And it will just give me all these numbers added up to more significant figures than I probably need, and we should get about 0.948. Very, very, very good probability this person will hit once in those 3 attempts. And finally, what's the probability of between 3 and 6, including those? And again, I could add these up here. That's essentially what we're looking at. However, again, I don't really want to do that. And so another option, which is maybe faster, especially when I have more possibilities to look at, is to realize that what I've highlighted is the same as 1 minus this part. And that part I just circled, I can use that cumulative distribution function. So I'm going to figure this out by indirectly calculating it, which it's going to be the same as 1 minus what I have circled, which is the probability of the hits being less than or equal to 2. That's how I'm going to figure it out, which, again, I can do quite quickly on a calculator. It's going to be 1 minus the binomial cumulative distribution function with 6 trials, 0.275 probability of success, and exactly 2 or less. And if you just calculate that, it brings me to about 0.211 probability, just over a 20% probability. Which again, you should get a similar number if you add all these up. Although again, what I have on my calculator screen here is more accurate because I don't have any rounding error. And it's probably faster. So just keep in mind going forwards, there's a distinct difference between the cumulative distribution function and the probability distribution function I mentioned here. And we just want to be aware of when to use one or the other.